So we were at this point. Okay, we did double bonds, we did multiple geometric isomers. So very quickly, let's try and finish this so we can do some past paper questions. Uh, so I told you that you will have what was geometric isomers. This was where's the this was geometric isomers, that you had a cis arrangement, you had a trans arrangement. Can't rotate the molecule around a double bond, which is why the H's would always be pointing in opposite directions. Over there, the H's are pointing in the same direction. So that's cis, this one is cis, trans, right? So we did that, and then we did unsymmetric alkenes, and I told you that an unsymmetric alkene is where the left and right side is different. So we did an unsymmetric alkene, and I showed you that if it has two double bonds, then two double bonds, they would have four different arrangements. There would be four different geometric isomers for this entire molecule. The first one would be cis, the second one would be trans. The first one would be cis, the second one could be cis as well. The first one can be trans, the second one is cis, or both of them are in the trans version. We did that, and I showed you all of them. Okay, the first one is trans, the second one is cis. These two, they look kind of the same, except direction of some of the bonds would be different. Like over here, the CH3 is pointing downwards. The CH3 is very similar on this side, but on the other side, the Cl is pointing downwards, but over here, the Cl is instead pointing upwards. So this molecule is different from this molecule shape-wise. Then we did a trans arrangement. This is different from this one. All of them are different. At least one bond is pointing in the wrong direction. Over here, the Cl is pointing upwards. Over there, the Cl is pointing downwards. So at least one bond is pointing in the wrong direction. So I told you that you could use 2 to the power n, and in that way, you can figure out the number of total geometric isomers that a molecule can form, where n is the number of double bonds. So if a molecule has 3 double bonds and all of them are forming, let's think of a molecule that has 3 double bonds, and all of
सर ये सिमेट्रिक में नहीं होगा सिमेट्रिक अल्कीन्स में?
नहीं, अभी तो we're talking about unsymmetric. I'm going to come to symmetric.
अच्छा, तो ये फॉर्मूलास में एप्लीकेबल नहीं होगा?
हाँ, this is only for unsymmetric alkenes. ठीक है, we wrote that it's only. So if I have a molecule and it's got 3 double bonds and all of them are making geometric isomers, all of them. Let's say there's an H and there's a CH3. This one is an H, H and H, and you got an H and you got an H and Cl. So if you focus on all the double bonds, all of them are capable of forming geometric isomers. Each carbon atom in the double bond is bonded to 2 different groups. Like if you focus on this one, this carbon is bonded to an H. On the right side, it's bonded to this thing. This carbon atom is bonded to an H. On the left side, it's bonded to this side. This carbon atom, 2 different groups. This carbon atom, 2 different groups. This carbon atom, 2 different things, right? So according to 2 to the power n, how many different isomers are possible for this? Geometric isomers. But how many double bonds are making geometric isomers? That's 1, 2, and all 3 of them, right?
Yes, sir.
So this one could be cis and trans arrangement. This one could also be either in the cis or the trans arrangement, and this one could also be in the cis and trans arrangement. So the way you're going to use the formula is that you've got 3 double bonds. So n is the number of double bonds that form geometric isomers. So that's the 1, 2, 3. So 2 to the power 3 is going to be 8. You're going to have 8 different geometric isomers for this molecule. Is that clear?
Yes, sir.
So you're going to have 8 different geometric isomers. And the way you're going to have 8 different geometric isomers is it's just going to be a combination of all of these. The first one is cis, the second one is in the cis form, and the third one is also in the cis form. So I'm going to make all those 8 different combinations. So the first one is cis, the second one is cis, and the third one is also its shape is cis. Or you could have the first one is cis, the second one is cis, and the third one is trans. So that's a different 3-dimensional arrangement. Or you could have cis, trans, cis, which would give you a different shape. Or you could have cis, trans, and trans. And then the first one would be trans, this other two could be cis, or you could have trans, cis, trans, or you could have trans, trans, cis, or we can have another one which is all of them could be trans. So all of them can be trans as well. So basically eight different combinations. Now, eight different geometric isomers are possible, and you can make for three. They're not going to really ask you about drawing any of them because it's going to be harder to draw them. So they know your limitation when it comes to drawing. So maximum, when it comes to drawing, they might just ask you about two double bonds, but they can ask you like how many geometric isomers are possible with this one. If you have eight,
So,
हाँ जी,
सर ये MCQs में है इस तरह से?
हाँ मतलब he can ask you if how many different geometric isomers are possible for this one. So there would be eight different geometric isomers. These are the eight different geometric isomers.
और सर वो क्या है कि like all the isomers and including geometric isomer थे, फिर क्या होगा?
फिर तो बहुत ज्यादा हो जाएगा, फिर तो मतलब इस केस में तो बहुत ज्यादा हो जाएंगे. मतलब if they ask you to draw the structural isomer as well, that would probably, I mean, they'll try to limit the question somehow, some way. मतलब इतना open-ended question नहीं होगा. It's going to be that they're probably going to sort of try and limit the question. ठीक है. But वो हमने किया था ना, we did the structural. I mean when you add structural isomers, I mean the number of combinations when you have more atoms, it just increases. It exponentially increases. So they're probably not going to give you that tough a question. I mean, you need a computer model to do that. But anyways, the formula is simple. If you have four double bonds, that all of them make geometric isomers, so it's going to be 2 to the power 4. There would be 16 different combinations of the molecule, 16 different shapes of the molecule, right? So that's one thing. And now the next thing is, so you just need to remember 2 to the power n. Is that clear?
Yes, sir.
So now the next thing is, what if the molecule is symmetric? So if I want to make this a symmetric molecule, what I can do is, I'm going to use the same molecule. What I can do is, I can just change the CH3 to a Cl, and it will turn into a symmetric alkene. So that's what I'm going to do. So if I want to make this a symmetric molecule. So one second. So let's say this molecule is symmetric. Now, at the moment, all four are different, right? This is unsymmetric at the moment. All four are different. The left side has a Cl, the right side has a CH3. So all four, if you look carefully, Cl pointing upwards, CH3 is pointing downward. When the CH3 is pointing downward, the Cl is pointing upwards, CH3 is pointing upwards, the Cl is pointing downwards. So all four are kind of different. There's no similarity. Like if you look at trans cis and cis trans, if I even rotate this, it would still look different, right? Like flipping around the molecule or rotating the molecule is not going to make it any similar. Like if I flip around the molecule, I've got a CH3 at the bottom. None of them have a CH3 at the bottom. So rotating a molecule will have no difference. It will still be a different molecule. I mean, this is different from all the others because there's no CH3 on the left side. Keeping it the other way around, it's still different. The bonds are pointing in the wrong direction. But things would change when this is symmetric. So this is, we're talking about symmetric alkenes. So symmetric alkenes So I'm going to change the C. I'm going to rub off the CH3, so make it symmetric so that the left and right side are the same. I'll put a Cl in its place. That's the only thing. And the molecule will become symmetric. So just a minor change. And they're all symmetric now. So there's a Cl. Over here, there's a Cl. And the bottom one, there's a Cl over here. And over here, there's a Cl. Now look carefully. When the molecule is symmetric, now if I flip it around, if I rotate the molecule, this one specifically, and if the molecule is symmetric, remember trans cis and cis trans, left to right, right to left, it doesn't matter. When a molecule is symmetric, the two sides kind of look similar. Like where's the symmetric molecule? If a molecule is symmetric, the right side and the left side are kind of similar. You go from left to right or right to left. If you're standing over here, you still see the same thing. If you're standing over here, you still see the same thing. So if you flip this molecule around, nothing would happen. I mean, it's going to remain exactly the same. So when our isomers became symmetric, these ones, trans cis and cis trans would mean the same thing. At the moment, they do look different, but they are inherently the same molecule. I mean, at the moment, they look different. Like the Cl is pointing at the bottom, the Cl is pointing upwards, right? The Cl over here is pointing at the bottom, the Cl over here is pointing at the top, right? So at the moment, they kind of look different, but if I just take this molecule and I flip it around, I rotate it, put it the other way around, I did not change anything. So all I did was I just changed it. So not sure what happened to the trans thing. Let me knock this off. So all I did was I just rotated it. Now notice, remember I did not make any change. I just flipped it around. Now notice everything is kind of the same. The Cl is pointing downwards. Just hold on 1 second. Achha, so just coming back to this, sorry. Now look at, if I flip this molecule, the Cl is pointing at the bottom. Okay, so it's the same, exact same thing. Over there, the Cl is pointing downwards. Over here, the Cl is also pointing downwards. So these two are exactly the same. The arrangement of the atoms are exactly the same. Is this idea clear? That if the molecule is symmetric, then trans cis and cis trans would be exactly the same. Whether it's trans cis or whether it's cis trans, the two arrangements would be exactly, they would exactly be the same. Is this clear or not?
Yes, sir, it's clear.
So just remember that and this is the issue with symmetry, that you make all four, you make trans cis, you make cis trans, cis cis, you make trans trans, but these two would be kind of the same. These ones, the ones that you flip around and they look exactly the same, they would be the same. So focus on these arrangements. These two are exactly the same. You flip the molecule around, it still looks exactly the same. That's the issue with symmetry. Cis cis, if you flip it around, it still remains cis cis, and that's a unique arrangement. Trans trans, you flip that around. I mean, the left side is trans, the right side is trans. You flip it around, it still is trans trans. So that arrangement is unique. But cis-trans, you flip it around, it becomes trans-cis. And in symmetric, flipping around a molecule would give you kind of the same thing. So these two would be the same. So in symmetric, you'll have 3 unique geometric isomers, not 4, because 2 of the arrangements are kind of the same. So 2 to the power n is not going to work in this case, as these two are exactly the same, which is why you don't have to write this one. Cis-trans and trans-cis would be exactly the same. Is that clear? Zaid, is this clear? Sidra, Osma, Mahad, is this clear?
Sir, I have a confusion. Cis trans, when it's flipped around to trans cis, it's not the same.
In symmetric, it is the same. In this one in unsymmetric, this was unsymmetric, right? This was an unsymmetric molecule, right? In unsymmetric, if the left one is trans and the right one is cis, and this is the other version, if this is the cis and this one is the trans, these two are inherently different molecules because the direction of the bonds is different. Like if you keep it this way, the CST is pointing upwards, the CST is pointing downwards, right? The CL is pointing downwards, the CL is pointing upwards over here. Even if I rotate it, it will still be different. Like rotation will not make any difference. They're still going to be different. But the rotation would actually make them more different because the CST is on the left side, the CST over here is on the right side. So they're both different. The orientation of the bonds or the direction of the bonds is different. So in unsymmetric molecules, no matter how I keep this molecule, it always looks different from that one. Is that clear? This first part, is that clear?
Yes, sir.
But all I did was I copied the same molecule and I made it symmetric. All I did was I took this molecule and the CST at the end, I replaced it. So I took this molecule. All I did was I took the CL, I replaced the CST over here with a CL, and the molecule became symmetric. I mean, there was a CL over here, and on the other side, there's a CL as well. So now it's symmetric. The left side and the right side of the molecule are kind of the same. It's got Cl and H. This one also has Cl and H atoms. And I told you that this was the cis version. This was the trans version. Let me write that as well. So this is exactly copied from the top, except that I made it symmetric. Okay, I changed the CST to Cl. And then I showed you that now if I flip it around, the trans cis, the first one trans, the second one cis, or the first one is cis and the second one is trans. Both of these arrangements would kind of be exactly the same. Because if I flip it around, these two are now exactly the same. Look where the CL is pointing. In the bottom one, the CL is pointing downwards. In the top one over here, the CL is pointing also downwards. Where's this other CL pointing? That is pointing downwards. The same CL is also pointing downwards over here. So they're exactly the same. The arrangement is exactly the same. The three-dimensional shape is exactly the same. The H is exactly in the same position. This H over here is exactly in the same position. This H is in the same position. The CL is pointing downwards. So is that clear? Is this then clear?
So,
Hanji.
Yes, sir.
so वो जो unsymmetric का था, unsymmetric के end में जाके अपने functional group change किया, क्या वो down like middle में वो change हो सकती है functional group?
नहीं मैं तो I just wanted to make it symmetric ना. मतलब
या सर,
functional
लेकिन मैं unsymmetric की बात कर रहा हूँ.
नहीं, इसमें मैंने कहाँ से functional group change किया? वो तो मैंने देखो उसको मैंने बनाना था वो मैंने symmetric molecule बनाना था ना. So I just changed the CST. But all I wanted to do was I did one example with an unsymmetric alkene, which is this one. I wanted to make this molecule symmetric, so I did another example. So वो जो है ना the other one, that's a totally different example. All I did
Okay,
was
sir, तो like बीच में symmetric नहीं बना सकते, like बीच में functional group change नहीं कर सकते.
कहाँ बीच में कर सकते, यहाँ पे कर सकते. Symmetric,
Okay, sir.
मुझे बताओ symmetric बनाना था तो इस molecule को किसना change करते if I wanted to make it symmetric? Either
Yes, sir. जो functional groups हैं end में वो same होने चाहिए.
left side and right side should be the same, right? So I could have turned this Cl into CH3. That would have made it symmetric, right? So this other example was for symmetric, and all I said was, okay, in unsymmetric, all these combinations are unique. Cis, cis, trans, 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 cis, cis, trans, they're all unique. But when you have a symmetric alkene, the combinations that can be flipped around are not unique. Like if you have cis trans, you just flip it around, but the condition is it has to be symmetric. The molecule has to be symmetric. So if you have cis trans, you flip it around, it becomes trans cis. So these two are kind of the same. So that means this is not another unique isomer. You're just rotating the same thing. So that is not, I mean, this one over here is not a unique isomer, and you should cut it out because you're drawing the first one again. You're just drawing a rotated version of that. You just have 3 isomers now, not this one. Is that clear?
Yes, sir.
And the same thing we can talk about. We can talk about 3 double bonds, right? If you have 3 double bonds, let's assume this is symmetric, like there's a Cl over here. Remember, flipping around a molecule, if it gives you the same thing, it's not a unique arrangement. So which ones are the same? But in unsymmetric, all of them are unique. But if this molecule is symmetric, if this molecule was symmetric, which ones would be exactly the same? Like if I take this one, if I take the first one is cis, it's cis, cis, and cis. If I flip it around, I'm still going to get cis, cis, and cis, right? So that's a unique arrangement. It doesn't match any one of them. So that's the first one. What about this one? If I flip it around, what do I get? I get trans, cis, cis. So these two are kind of exactly the same. Is that clear?
Yes, sir. Sir?
So these two would be the same. They're going to be the same for if molecule is symmetric.
Sir, वो cis trans cis नहीं होगा फिर?
What's that?
जो third में.
Cis trans cis is unique. Like if I flip it around, what I'm going to get is again cis trans cis. And there's no other combination that gives cis trans cis. Is that clear? So that's unique. Clear?
Okay, sir.
So what about the next one, like cis trans trans? If I flip it around, what do I get? I get trans trans cis, right? Which is this one. So that means, what that means is that these two are also kind of the same. Is that clear? And
Yep.
and this one looks unique. Trans cis trans. If I flip it around, it's still trans cis trans, and that's kind of unique. There's no one else. Trans 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 is also unique. If I flip it around, I'm still going to get trans trans trans, which is no one else is trans trans trans, right? So instead of getting 8 isomers, what I'm going to get is I'm going to get 6. So in unsymmetric, in unsymmetric you have 8, but in symmetric you're going to have 6. They're just 6 unique arrangements because 2 of them are not. Like these 2 are repetitions. These 2 are also repetitions. They're just flipped around versions of the same thing. Is that clear?
Sir, what about cis trans cis and trans cis trans? Why aren't they?
They are different. Like if I flip around cis trans cis, what do I get? I still get cis trans cis.
Oh, okay.
I mean, if I go from left to right, it's cis trans cis. If I go the other way around, it's still cis trans cis. So that's different from this one.
Oh, okay. Understood.
Okay. So basically, when you have a symmetric alkene, what basically happens is you go from left to right, or you go from right to left. If it reads the same thing, it's the same thing. If cis comes first, trans comes later, or if you go from the right side, it's trans coming first, cis coming later. It's basically the same molecule because the left and right side are basically the same. So which is why, so coming back, I'm just going to sum this up. 2 to the power n is going to work if you have an unsymmetric alkene. Every arrangement is going to be a unique arrangement. But if it's a symmetric molecule, then these two, trans and cis and trans, they're going to be the same exact arrangement. They're not going to be different arrangement, which I showed you over here. When I made the molecule symmetric, when I did it with this, when I did the same thing, but this time the molecule was symmetric, we figured out that this arrangement and this arrangement is exactly the same arrangement. So which is why trans cis and cis trans were kind of the same thing. So your number of isomers dropped to 3 instead of 4. Right? Is that clear?
Yes, sir.
I said, anyways, but you
Yes,
don't.
sir.
I said, so it's very rare that you do get questions. You've got questions about symmetric alkenes, but most of the questions, most of the common questions, are about just drawing. I mean, most of the questions would be about one double bond and one cis trans, not about multiple. There are questions about multiple double bonds, but most of them would be about just one double bond. For example, this one will have 2 isomers. It's going to have a cis and it's going to have a trans version. So most questions would be about a single double bond. But you do get questions on this as well. Now the next one is we're going to do, and also remember, whenever you have isomers, whenever you have isomers are physically and chemically different. Like I told you that the physical properties and the chemical properties are going to be different. If we go back where we started off, like if you look over here, this molecule, one of them is polar, one of them is non-polar. Like Cl on opposite ends, the dipoles would cancel out because the Cls are pulling electrons or attracting electrons from opposite sides. So there's not going to be any dipole. But if the 2 Cls are in the same direction, then there's going to be a dipole because both Cls are pulling the electrons downwards and the bottom side would become negative. Is that idea clear?
Sir,
Yes, sir.
सर ये कौन सा स्टार्ट से एक्सप्लेन कर सकते हैं
कौन सा
ये जो आपने अभी डाइपोल्स को बताया
नहीं मैं एक्सप्लेन करो कि whenever you have an isomer, ठीक है, we did structural isomers. In structural isomers, that's a drastic change. Like we did structural isomers, everything could be different. Like if I go back in structural isomers, like we made structural isomers for this molecule. Everything could be different. You could have a carboxylic acid. This could be an aldehyde. It could be an alcohol. This is an aldehyde with an alcohol. You can turn it into an ester as well. You can turn it into a diol. So in structural isomers, you can rearrange atoms and everything can be different. And the physical and chemical properties would drastically vary. But I'm saying that even in stereoisomers, where the difference is slightly lesser because you're not rearranging the atoms. All you're doing is you're just rearranging the direction of the bonds. So even in stereoisomers, the properties and the chemical and physical properties are going to be different. वो पता है कि dipoles किस तरह form होते हैं? Dipoles are formed when you have electronegative elements. In this case, you have Cl and you have Cl. It's pulling electrons upwards. This is pulling electrons downwards. So क्या होगा? Both forces of attraction are going to get cancelled out because the 2 Cls are at opposite ends. Is one clear?
Yes, sir.
वो ऊपर खींच रहे नीचे खींच रहे ना तो electrons किधर जाएंगे उधर ही जाएंगे they're going to stay right wherever they are because the forces of attraction are going to get cancelled out. While if the first molecule is going to be polar, the cis version would be polar. The Cl is pointing downwards. This Cl is also pointing downwards. So both Cls are trying to pull electrons downwards in the downward direction. So they're not cancelling each other out. Both of them are pulling electrons towards the bottom. So this would be negative, this would also be negative. The top side would be positive, this side would be positive. So this would be a polar molecule, while this one is going to be a non-polar molecule. So the idea is you have all types of geometric isomers. Even if the variation is less, there would be differences in physical and chemical properties. Is that clear?
Yes,
Yes,
sir.
sir.
And then similarly, you have so they might ask you about that thing you would have to guess at the point because there are all sorts of molecules. They might ask you what are the differences between their properties. So I mean, based on what the molecule is, you would have to guess. And not only that, remember, I'll just give you some importance about stereoisomers, specifically geometric isomers, but the same applies also to optical isomers. That biological, this is very important in biology. Biological structures are not as simple as this tiny molecule over here. Biological structures are really big. I mean, we are basically made up of carbon atoms grouped together, bonded in something similar to this. So just imagine that if only having a molecule having two double bonds can have four different types of arrangements. Imagine a molecule like, let's imagine the human skin. Let's say the human skin has a lot of double bonds and all of them are making geometric isomers. So the number of combinations, if you do 2 to the power n, that would be a lot. Like if I have just four double bonds, what is 2 to the power 4? I think that's 16. 2 to the power 3 is 8. 2 to the power 4 is 16. So if I have four double bonds, the number of possible arrangements would exponentially increase. There are 8 different versions of this molecule. Now, biology is all about the shape of the molecule because imagine this as the building block of the human body or any organism that's organic, whether it's plants or trees or animals. So imagine you're building a structure in a human body, a cell membrane or a muscle or anything. The number of possible arrangements are many. And it's like building a house. Like if the direction of the wall of the house is in some other direction, the entire structure would be different, right? I mean, let's say you're taking this tiny block and you're trying to build a bigger structure on top of it. So if the CL is pointing downwards, but in this molecule, the CL is pointing upwards, the bigger structure that's going to be formed is going to be totally different. So biology, it's very important that when you're like all the information on how the structures are built, they are stored in DNA, and from there, translation and transcription happens, and the human body or the human cell starts making proteins and different structures. So it has to always make the right type of structure. Any other arrangement, like for example, if you're trying to make the red blood cell, if this is the structure, then the cell has to get the structure right. If it makes any other structure, then it would be a different arrangement and the cell will have a different shape. So is this idea clear that how important this is in biology?
Yes, sir.
सर
Yes.
सर इसके अंदर टेम्पररी और परमानेंट डायपोल आ सकते हैं
किसमें?
ये जो स्ट्रक्चर्स हैं एल्कीन्स के
वो तो इंटरमॉलिक्यूलर फोर्स है ना, वो तो अलग कहानी है, लेकिन वो होंगे ना वैसे हर मॉलिक्यूल में होते हैं.
ओके सर
ठीक है, अभी हम उसको डिस्कशन तो नहीं कर रहे. इंटरमॉलिक्यूलर फोर्सेस तो होंगी, we'll talk about that later. But this one, I just repeat, okay, biology, it's very important. Okay, the human body has to get this. And the reason I'm actually describing this is, okay, why do you study organic chemistry? Because when you study organic chemistry, they're going to link this with, there's going to be a very general question on this. They're going to link this with medicines, because the reason we study organic chemistry, it's like studying viruses, animals, organisms, bacteria. That's all organic. That's all a bunch of carbon atoms bonded in different ways. The human being is basically a bunch of carbon atoms that's got some oxygen atom in it, some nitrogen atoms. They're all bonded in different ways. Glucose, etc., carbohydrates. They're all carbon atoms. So that's all organic. And it's something, I mean, we are something like this. We've got double bonds, we've got these different arrangements. There's probably just going to be one arrangement that's going to make a human being. The other ones are probably going to make some other structure, which is why you've got a variety of organisms, because the shapes would change. Because the main building block can have many different shapes. So the important thing here is that nature has figured out a way to make the right structure every time. Whenever your body makes a red blood cell, it always makes the right type. Like if it needs a double bond in the cis arrangement, if the second double bond in the molecule has to be in the cis arrangement and the third one has to be in the trans arrangement, then the human body always gets it right. It never makes unnecessary red blood cells having different structures. It always makes the right type. So so nature has figured that out. So they're going to link this with medicine. Natural medicines, they don't have this problem because, like, if you take a medicine like a herbal medicine, uh, it's not going to have any side effects because the type of chemicals that it will have will be only one of them. It's not going to be all of them. The problem with medicine, like the artificial, not the artificial, but the medicine that is prepared in the laboratory. The problem with that is that if I go in the lab and I try to make this molecule myself, human beings are pretty bad at making this molecule. Like if I want to make a particular type of medicine, and that medicine, the first one has to be cis, the second one has to be cis, and the third one has to be trans. We are pretty bad at doing that. Nature is pretty good at doing that. Like your body is constantly at the moment, it's producing lots of chemicals, lots of structures like these. Your skin is growing, your hairs are growing, everything is happening, but it always gets everything right. It's very hard for us to get it right. We go to the lab, we try to make cis, and trans, but it's very hard for us to make cis, and trans. We might end up making trans, cis, and trans. We might end up making trans, and trans. So getting all three arrangements in the exact right order that we want it to be, that's pretty hard. Do you get my point? Is the point clear?
Yes, sir. Yeah.
So I'm just trying to link this point to side effects of medicine. Herbal medicines, they don't have a lot of side effects. I mean, they might be ineffective, but they don't have side effects. Why? Because nature always tends to produce one type of geometric or stereoisomer, and it always gets it right. When we try to make one type of geometric isomers, we kind of, at a lot of times, we get it wrong. So imagine this one tiny molecule. Medicine molecules are a lot more complicated. Imagine this molecule has 8 different shapes. You're going to go to the laboratory and you're being asked to. That's why, like, if you take a vaccine and they're developing a vaccine for a virus, why do you have side effects? The reason you have side effects is that this particular arrangement will work, and maybe this arrangement, the trans-cis arrangement, might cause some side effect. It might react with the membrane or in your heart. It might do some strange stuff. So the problem is with medicine is that because of stereochemistry, when humans make in the lab, they make medicine molecules. We've gotten pretty good with it, but we're still struggling with some. Like we might make 90% of this, the right one, and maybe there would be 10% of this also present, and that would cause side effects. And Haji.
सर इसके अंदर तो ये भी हो सकता है कि म्यूटेशन कॉज हो जिसकी वजह से लाइक बॉन्डिंग चेंज हो जाए.
But right now I'm not talking about changing the structure. I'm just talking about even if the arrangement is the same, everything is the same. The stereochemistry, there would be 8 different possible structures. Only one of them would probably work. If you take a Panadol or a paracetamol medicine, the paracetamol structure probably has stereochemistry. It's going to have this structure, but there would be 8 different shapes of that structure, but only one of them would work. The other ones might be either not working or they might cause some sort of side effect. Is that clear?
Yes.
So I just wanted to link this to drug delivery, that which is why you need higher doses, because when a human makes this molecule and he wanted to make this molecule, maybe 10% of this molecule is produced, and the rest are all these other other stereoisomers which don't work. So which is why your doses, you need higher doses. Side effects are produced because of stereochemistry. A lot of side effects are produced by stereochemistry. Actually, all side effects that medicines have, they are because of stereochemistry. Is that clear?
Yes, sir.
So just this minor point, and they might just ask you like, why is stereochemistry important? So it's important because getting the wrong one would have very dangerous side effects. So let's continue tomorrow. We'll do optical isomers tomorrow. That's a simple one. Okay? So we'll finish this and we'll do past papers. Okay, everyone.
खुदा हाफिज़ sir.
Allah Hafiz.